On this episode of the show, I have with me Joseph Krause. He is co-founder and CEO at Radical AI, and we're going to be talking about how science happens, and we're going to dive into how science has happened for the longest period of time, and, well, we're going to talk about how some of those quote-unquote mistakes have led to some of the most impactful innovations that we've seen, and we're going to be talking about the limitation around the current science model, where companies are finding collaboration as a challenge, and then we're going to dive straight into what's happening in the future and how science is evolving. Joseph, thanks for taking the time.
Amir, thanks for having me. Super excited to be here and excited to dive into where the future of science is going.
Absolutely. Before we start, if you could set the context of what you guys do at Radical.
Yeah, absolutely. So at Radical AI, we are really creating a new form of scientific discovery where we are focused on removing materials as the biggest bottleneck to our most important industries. And the way that we do that is this interconnected materials flywheel that includes both an AI engine and a fully robotic self-driving lab. And together, those things form this flywheel that will enable new discoveries and therefore enable new industries.
Fantastic. All right. We got a lot to unpack here. So we're gonna start at the top. Actually, we'll go in the Wayback Machine first. But obviously, science has been around for a very long time. We won't put years.
That's right.
I dare not say how long because somebody will want to correct me. So it's a very long time. I've done this long enough to know that I don't use something as a number unless I know. And it's happened a particular way. And maybe you can help set the stage in explaining, if somebody's not familiar with how innovation happens within science and laboratories, what does that way, how has that way traditionally looked? And maybe we don't want to go too far in the past, but if you could give us a little context.
Yeah, sure. So I think, and I'll speak from my own experience as well. I'm a material scientist by training, and that's what I was doing before I got into the tech and venture ecosystem. So the way I like to describe it is really a serial-based process. And what I mean by that is just like you classically learn about the scientific method, what we'll do as research scientists is when we look into a new space, we'll go and read publications. We'll understand what has the field worked on, what have they discovered, how can I get up to speed in new discoveries, and what is state of the art today. We'll look into different industries as well as different, even just searches in textbooks or patents and other databases around, okay, where is technology and how is it being used in real commercial applications? And then from there, we'll make a new hypothesis, right? Hey, what should I make next? And we take that hypothesis, we make it in a lab, we test it in a lab with a bunch of characterization tools, we analyze all of those results, and we come way back to the beginning of that process and rethink, okay, given everything I just learned, how close was I to my hypothesis or off, and repeat that process over again. And the reason I call it serial is all of these steps happen sequentially, one after the other. And the problem with that is, number one, it's incredibly slow. And two, you actually cannot draw connections and correlations between all of those things individually, just because you're limited by the human brain, right? I can only read so many research papers at a time. I can only run so many experiments with my two hands, and I can only analyze so many pieces of data simultaneously to really drive value. And so that's really the way, at a high level, the scientific process happens today. What we start to do is actually change what that looks like. And we do that in a parallel fashion, where rather than running all of those things sequentially, we run them simultaneously. And so while our AI might be making thousands of new hypotheses, while our self-driving lab might be fabricating or what we call synthesizing hundreds of new materials, and while we might be analyzing thousands of different data points and experimental characterization outputs, we can draw corollaries between all of them at the same time. And remember, AI is a lot more powerful than we can be. Our AI scientists can read 70 million publications in minutes. I don't think I've ever read 70 million in my life, maybe let alone a million, maybe let alone 100,000, right? And so you start to get this order of magnitude scale in the tasks themselves. And then the way you're able to draw connections between those tasks are really impactful. And again, you build this parallel process that has all of these things ongoing simultaneously. We think there's a lot of knowledge to be unlocked in there. Absolutely.
When you talk about the serial nature of the way science has been, I guess typically we hear about science with what we see at the end. We don't see the science process. And we see two types of results. We end up seeing what is probably a lengthy science process where there's intent and things happen. We then also hear about these situations where science is created by accident, and we hear those great stories of lore. I guess, and obviously, science with intent is different. Science by accident is maybe different. When we look at those two and we look at historically how humans have found innovation, obviously we'll tie it back into AI, but looking at how we've typically done with our breakthroughs and the time that's taken and the randomness of the ones that we were unexpectedly now in good fortune having, talk to us a little bit about that dynamic, because it seems like the more famous ones we always hear about that happened by accident, but that's not the way most of our stuff's coming to market, I'm assuming.
Sure. Yeah, there's absolutely a lot of successful work done as well. So they both come back to the same thing, which is actually the negative results, as we call them, or mistakes, as you said, and their part in the scientific process. So I'll talk about both. On the negative side, or the mistakes first, this one's quite simple, right? If we accidentally bump into a property that we didn't expect, or something as simple, I actually did this in grad school, you knock over a beaker, or you put too much concentration in and see a result you weren't expecting. That's that traditional mistake that you hear in the science, and you kind of make a new discovery or something really interesting and you go down that path. That one's understood. But on the successful research, the same process is actually happening. It's just not the mistake that is the discovery. It's the collection of all those mistakes that lead up to making the discovery, right? And if you think about it as a scientist, 90% of the work that we do doesn't work. It is part of this trial and error process I've just walked through of testing hypotheses. And it's really all of those negative results that are imperative to the 10% of things that do work. That's how we make novel discoveries. And one interesting thing about science, which I'm sure we'll talk about, is the lack of capturing of those negative results, right? We don't really publish on those results. They're not the successes. We don't talk about them. Even within research conferences or in the community, we really focus on the things that did come out of the lab, not are still in it. And even if there's direct research collaboration, right? Yourself, Amir, and myself are working on the same project. Well, we have no idea what each other does in the lab and can't really build on top of that. So we might repeat a lot of the same experiments to build that intuition. And so actually capturing all of these negative results is crucial to building the data sets that we need in AI. And we can certainly come back to that because Radical is focused. But as you go through the scientific process, you build what makes someone a great scientist, right? This intuition around, hey, look, I've either published the top papers on the things I've discovered, I've read the top papers on the things other people have discovered, and if it's not in one of those two buckets, I've done 30, 40, 50 years of science, right? To know where things are going in a certain field. All of that is truly just a collection of negative results or experiments that didn't work that lead you to that breakthrough. And so I actually think most breakthroughs come back to that core concept, whether it is accidental, meaning I didn't think that was going to be discovery, or it was a combination of those that led to the discovery. It both starts with the ability to test new things and have those things fail compared to what you thought they were going to be. And it all starts from there.
Absolutely. An interesting example, I think everyone will have heard of, obviously, Edison and I haven't failed. I just found 10,000 ways that
Absolutely
won't work. When we think about that, obviously within the context of one person or one lab, because I think this ties into what you just said, being in control of those 9,999 other ways that didn't work would know what has not worked. And I think even when we think about what you just said is what hasn't worked, if there's another group of scientists working on the same problem, they ran the same exact parallel, maybe that they would have hit to the 10,000th and been like, we got it. Or they gave up at the 6,000th and they're like, we didn't. When we think about that collaboration within science, and you kind of alluded to it, but I want to go a little bit deeper in there, is do the labs talk to each other? Is the data shared? And what's the magnitude of scale of people potentially doing very similar things and trying to, again, rule out things that are not working?
Yeah, so A complex answer, unfortunately, because the answer is both yes and no. And I'll talk about what I mean. So the yes part of the answer is that people are aware materials are fragmented, and there have been real attempts to solve this fragmentation, right? The Materials Genome Initiative, which was started, I think, back in the early to late 2000s, was very much around orchestrating around infrastructure, trying to make utilized data, and really thinking about, hey, how could we learn from what all the national labs in the United States are doing? That never really panned out, unfortunately. And actually, you see in the AI policy that just came out from the current administration and the Office of Science and Technology Policy, there's a call again to focus on data infrastructure and really the accessibility for the community to have access to that data. I think you're feeling that push because of the machine learning wave, and that's really important, missing piece in materials. So yes, people are aware and have tried to share. The no of this answer is it hasn't been successful. Materials are just such a fragmented industry, right? I always like to describe two paradigms inside materials. You have one paradigm that is entirely focused on just driving our understanding of science, right? Academia or national lab, for example. How do I discover new things? And there's not much focus on commercialization. And then the other side, you have kind of corporate R&D, very much focused on optimization. How do I drive 1, 2, 5% performance gain inside the systems I have today? And they really do that candidly because they're reporting to Wall Street, and it is what it is. That's what they have to do. So in the middle is this wide open white space to really focus on novel discovery, entirely focused on commercialization. And of course, that's what we believe at Radical AI is the opportunity and what we're working on. But given that fragmentation, the ability to share actually isn't even possible in some cases. The person doing discovery in academia might never know, talk to, or even interface with the person running the manufacturing lab at Dow Chemical or BASF. And so much of this information really gets lost in translation, for lack of a better phrase. And so it's not even from an effort of not trying. It's just from this natural fragmentation of the industry that it's very hard to capture and build on existing data sets when there aren't any.
I mean, that certainly makes sense. I guess the follow-up to that would be, and you mentioned obviously it is fragmented, the Wall Street component, but obviously it's exceptionally valuable if you can discover a material. I mean, you will forever own a patent. I don't know if forever, but you'll own a patent. It'll be licensed. You'll make a lot of money. We've seen the military, we've seen NASA come up with these type of materials that come to market. We don't necessarily focus as much on the individual manufacturing companies. We know some of them. I'm talking about it from the outside looking at. You're deep within it. Talk to us about the economics, because if I'm listening, I've heard that there's no collaboration. If I'm slightly cynical, I'd be like, well, of course, no one wants to share. I want to make money. Forget about sharing. So how do you reconcile the fact that there isn't collaboration, which would help society, but also then companies want to ensure that they're maximizing their opportunity for profits?
Yeah, very good question, because in material science, there are two core problems. Number one, the IP of a new material, yes, exists in the structure and the patent you get from that, but also in how you process it, or put simply, how you make it at scale. And a lot of that information is kept trade secret and really internal to the company. And that's the bread and butter, right? How do I make this for a better cost and at a larger scale than my competitors? And so the first problem in materials is that capturing the value is a CapEx intensive process if you're going to vertically integrate, and takes a lot of trial and error in multiple sections of discovery. It's not just making a new material from the patent and like composition perspective. Then you have to go through this whole iteration process on the manufacturing side. How do I optimize the temperature? How do I optimize the pressure? I mean, what type of reactions do I need at a batch scale that change the outcome? And so all of these things actually are very hard to do. And so that really points towards wanting to own the manufacturability and processing of a new material. And the second problem is really who is working on materials. And what I mean by that is a lot of the work that we have seen from corporate R&D is again focused on this optimization problem. And so one of the problems with materials is that as they become commodities, there is really a race to the bottom on certain cost or supply chain constraints that companies want to consider when looking at making a new material. And that is limiting to actually enabling new industries. If we think about landing on the surface of Mars to purposely pick one that's out there, well, we don't have current TPS that's reusable to take off from the surface. And we certainly don't have solar panels that we're going to bring with us up to the surface. We need to remake them when we get there. And so there's these ideas, who's working on those materials that are actually going to enable a space habitat on the surface of Mars? Not Dow, not DuPont, or not BASF to my knowledge. And so there's this kind of misaligned incentive around all of the value is in discovering something new and scaling it. But all of the focus from the big companies who have that processing and manufacturability is focused entirely on optimization. They don't want to do new discovery and scaling. And so you kind of have this crossroad where we all want novel materials that make new industries and actually power the future of technology. But the only people capable of capturing the value, aka manufacturing it, aren't investing in discovering those materials. And so we get stuck in this paradigm where we don't have novel materials, and the ones that we do have become a commodity-based business, and the margins start to shrink as they become more widespread in the market. There's a very tough business model if you're not vertically integrating with new materials in mind. And as you can probably guess, that's a big thesis area for Radical AI.
Yeah, I mean, definitely. And I want to actually jump forward a little because I think this in itself, we could probably spend the whole time, but I know people are going to be like, yeah, we tease the future. We gotta get there. And there'll be some questions there as well. You mentioned the fact that serial has been the way science has been done, especially in materials. Parallel is the future. You referenced AI. Can you maybe give us a little bit more depth? And you mentioned self-driving labs in there as well. And before I start asking questions about the future, I want to make sure everyone understands when we talk about parallel, initiatives, we talk about self-driving labs. What does that exactly mean?
Sure. So self-driving labs are about building scientific research facilities or labs that are entirely run by robots and automation, with no humans inside that loop. And so what you do is you actually remove the human scientists from being in the lab and running the experiments and put them outside the lab where they are watching the experiments be run and then looking at the analysis as it is done in real time. And they can actually weigh in on and help impact kind of the discovery loop as it's unfolding. And so where is AI really impactful today? What is this new future of science? Well, it's actually a combination of an AI engine and the self-driving lab. And they build this connected flywheel that comes together to enable us to shorten that timeline to discovery and definitely reduce down that cost. And so on the AI engine side, AI is all over the place inside material science, from reading publications, like I mentioned, indexing the web, understanding information, to actually running and simulating quantum chemistry calculations like DFT. We do this with what are called machine learned interatomic potentials. They're run by graph neural network architectures, all the way through to what is the holy grail of AI materials, inverse design. And this is where you actually go to an industry, you understand their problem, and you inversely design the material from that. This is where we really want to get to from a scientific process. And that is mostly diffusion or language model-based technology today, or generative, as we call it. So on the AI front, just in discovery, it's producing new materials that we should go try in the lab. And so that AI engine will send those materials into the self-driving lab, which will start making those materials and then running a bunch of characterization tests on them. And what that means is it learns, hey, what is the material that you made? And then what are the properties that it has? Is it very strong? Is it very conductive? Is it ductile, et cetera, depending on the industry that you want to target for. And there's a really important piece that connects this flywheel together that we think is the future. As I mentioned earlier, when you're running all these experiments, you're capturing this experimental data that is not captured today. When we're training these AI models, we do not have experimental data sets to train them on. So by running a self-driving lab, you can start to get to 50, 60, actually 100 experiments per day. And so you're doing 33,000 experiments per year in a single lab. That's more experimental data than probably in a certain field has ever been captured after you move over a couple of years' time, bringing it all back into the AI engine. And so now you have a model that isn't only taking computational data or simulation data, but is using real world ground truth data in the experiments. And this is, of course, where the flywheel gets connected. And so both of these, the AI engine and this self-driving lab, kind of feed off one another, where one is sending materials in, the other is sending results out, and those two systems work in concert, optimizing against the new material for the properties that you specified. That's the future of scientific discovery that we see.
We'll put a pin on the reverse engineering materials in a second, because I think there's a couple things in between there. I guess what keeps, you mentioned some of the big, manufacturing, DuPont, BASF, Dow. What keeps them from saying, you know what, we have some, I don't know, some of them have been around for maybe 100 years. I mean, we've been around for a while. Let's leverage AI to do this. What would be because obviously you guys are starting ground floor building for purpose systems, ecosystems, self-driving labs. What is it that keeps them from trying to maybe move into that space?
Good question. The first answer is cliche, but incredibly true. Innovator's dilemma. When you look at what Dow Chemical is working on, they are making billions of dollars on materials that they already have in market today. And they report quarterly on how they're driving better margins to do exactly that. The ability for them to take a step back and actually develop new materials for hypersonic flight or nuclear fusion is just too risky to the current business model they have today. Classic innovator's dilemma. And so they can't do it. Then the second reason is a talent thing. When you talk to those companies, and I've talked to quite a few of them, this is their words, not mine, although I think it's true. They're not hiring the best machine learning scientist in the world, because machine learning scientists don't want to go to a 100-year-old company that is probably not on a coast and is also probably not focused on the problems that they care about. They want to go to a young company that is aggressive growth, that is tackling real hard challenges, and that the result of their work doesn't end up in a Post-it note or a bottle cap, but ends up on the surface of Mars or in every nuclear reactor in the world. That impact potential is rare to be able to find. And what is so unique about materials is that regardless of what industry you care about, automotive, aerospace, manufacturing, defense, climate, energy, semiconductors, like we always say, most important industries in the world are all a direct result from materials R&D. And so if you can work on technology that can truly impact every person on Earth, there really is no greater mission to go after. And so where do those people want to go? They don't want to go to optimizing adhesives for Post-it notes or, novel polymers for paint color. They want to go to the places that are working on creating materials that really enable this future that we all believe in. And so when you have this innovator's dilemma of they can't take risk, and you couple that with not even having the talent to take that risk, you just get locked in a place that they cannot innovate at the speed or the efficacy that an early stage startup could.
Absolutely. I mean, that certainly makes sense. And I guess when we talk about this parallel nature of where science is headed, where the innovations are going to come from, up till now, we've been doing this serially. I understand that. We're seeing trial and error. We're not capturing enough data. We don't go through enough permutations to know what will or will not work. As we start going through these parallel processes, you said 33,000 experiments in a year out of one lab is more than maybe an industry has throughout its whole course of existence potentially. When we start bumping into, part of the term, you can correct me on the scientific term, bumping into things that are interesting, we find some material, I guess based on the frequency of that, is there a gap between going, we are getting a lot of quote unquote viable materials, and then going from viable material to real material, and also then finding a use case for the material because maybe there was some unintended components. What happens there?
Yes. So great question. And this is partly where inverse design is so interesting on the machine learning side. So most times in materials, a lot of the innovation or the novel materials that we work on are scientifically interesting. And for good reason, they have some property that would be very cool to optimize for. Conductivity, it might be a really good one in the semiconductor field. But they don't originate from the commercial side, right? Where they were hearing the problems they actually have and the materials that they truly need to solve them. And so you actually get to this place where you make a new material. It takes a tremendous amount of effort, time, and capital to do so. And then you actually go out to market, or you go to look at who has interest in that material. And they're like, not really. That uses something in our supply chain that's forbidden. That's at a cost curve that we can't afford. That just actually doesn't solve our problem. We didn't really care about ductility. We cared about, conductivity. And so you didn't really answer the problem that we wanted to have. And so kind of backwards approach really is popular, or really, I would just say, really prevalent inside the scientific process today. And it makes sense when it's coming from academia, right? Their job is not to answer customers' problems. Their job is to drive our understanding of science, to develop new things. And this is, why it's so hard to think about how to go full stack. Because if you're going to do so much discovery, how do you make sure you tie that into commercialization? And that is a really important piece of doing everything from inverse design and where the AI can really make impact there, to actually thinking about where to dive in when you start, as you mentioned, bumping into a really interesting material in the lab. And what AI really enables is what in our loop is called property-driven optimization. And so rather than doing the process I just mentioned to you, which is I'm going to make a new material and shoot in the dark and see who's interested, I'm actually going to industry and saying, hey, what are your top 3, 4, 5, 6 problems that you're trying to solve and isolate for in a novel material, right? Is it ductility? Is it hardness? Is it conductivity? Is it cost or supply chain? What are those things for what application? And we can take all of those things and actually train the model to optimize against all of them. So that as it's predicting a new material, when it does the characterization and analysis of that material, it can look back on what its design specs were and calculate the delta and optimize again to try to get closer to that. And what that enables you to do is if you accidentally bump into a material, or not even accidentally, you get to a place where you start hitting materials that have those design specs, well, one, it's going to register and it's going to actually be able to find those materials. It's going to, hey, material 121 is really interesting. It has the hardness we're looking for. But then 2, pull that material out and start running campaigns on versions of that material specifically. So rather than optimizing against the whole space, which it just did to get to this 121 alloy, now it can start looking at the other criteria, the cost, the supply chain, the conductivity that it's complementing this ductility. And then you can continue to optimize in that very specific space. This is why throughput's so important, Amir. If I was doing that as a human scientist, the process I just described to you is probably a year, maybe more. In our lab, that's maybe 3 to 5 days at max to be able to do that, capturing all the information as well. So if I can do that fast, and I can continue to optimize against the constraints I'm setting from industry, well, now I can really bump into, directly to the question, the materials that are going to solve real commercial problems. And this is why I talk about this flywheel being so important. If you take any piece of that out of the interconnected circle, it's very hard to be able to answer what I just did to you, because if you're just doing throughput, well, you might not be learning anything or you can't optimize. If you're just generating new AI materials, you might not be able to test them and actually confirm they're what you think they're going to be. So it's really this interconnected process that allows you to do this inverse design so you can optimize against properties, so you can deliver new materials to an end industry. That is the holy grail of materials discovery. That is exactly what Radical AI is building today.
Interesting. A left field question, because my mind has to drift left field once, at least during an interview, and this is the left field question. When you're going through this process, and I understand now the inverse process is certainly advantageous to actually using the lab to actually hone in on what you really need. and we talked about IP patents and how important those are. If you are accelerating the rate of product discovery, material discovery, and potentially you could customize, once we find it, if one company wants a certain version, another company wants another version, the patent component, I guess historically, it's very valuable to defend because lots of people would be chasing that and they go, oh, well, we can stop putting our efforts towards that because they've already got a defensible patent. We don't need to invest there. And then the company has the breadwinner. In the model you're looking at, I guess it's maybe multiple questions in there, but one is the value of the patent. The second, what happens to what a patent really could mean? Because if we are going, well, here's product one, and then I've now made product one through Z variations because every company had a specific customized component to that, still met the standards of what it is I guess in the scope of patents and what we've seen historically and what you're presenting in the future, what happens?
So I do think you're correct. The value of the patent begins to erode. I don't think people will stop pursuing them. I think Radical will try to patent the new materials that we develop. Yes. But again, I come back to that processing piece where that's where all the really juice for the squeeze is, right? Meaning you can patent the coolest material in the world. If you don't know how to make it at scale, then no one can buy it. And you'll run into this, and you do see these companies that have tried licensing as a business model. And it's kind of getting at what you mentioned, which is, okay, let me try to get as many discoveries as possible. I'll patent a lot of those discoveries, and then I'll license them out to different companies that want to use them. And the problem is those companies still have to figure out how to make it. Even when you license the composition, right? They have to go process it, understand the conditions, know how much they can make, what's the cost to make it. So after 2 or 3 years, those companies start saying, well, you know what? Let's maybe reverse engineer that patent or that license and see if we can get something similar that's not, where we have to pay royalty. And you'll watch your royalty revenue start to go to zero. And so unless you're coming up with hundreds of patented, valuable, super exotic materials per year, that's not going to scale. And this is why if you look at the big material companies today, almost all of them, if not all of them, sell materials. Dow, BASF, Materion, etc. Carpenter, even in very specific spaces like alloys, they sell materials at scale because all of the IP is, yes, in the patent and the composition, but then also in how you make it and process it at scale. And so you need to have both of these things together. So to your question, yeah, I think the more and more you can make quicker discoveries, the more and more those patents become less valuable, but the more and more the data of how you made it become more valuable. And this leads to vertical integration. If I run 10,000 experiments and capture every single parameter in that process, once I make that new discovery, I can use all those parameters when I go to manufacture and scale. And yet there's still some optimization. There's still some things you have to figure out. Absolutely. But you're not starting from ground zero, which is typically where they start today, ground zero or level 1. You're at level 9, level 10 of 15. And so you can move much more quickly through this scaling, process and continue to receive the end value. So what we actually think is you'll be able to actually have more manufacturability across multiple systems versus being siloed into a single material class or system today, which we're very excited about, kind of the impact that can have, not just with what Radical can do, with all the companies inside materials are going to start to move towards.
Fantastic. I actually was, as you were finishing that, I was like, you guys are the data of material sciences because you've referenced the data now several times. Obviously, the vertical integration is key because I understand now without the material manufacturing, that is a gap, understanding that end to end, just being an AI model. And it is interesting. The more you've spoken about this, the more I go back to thinking about that as an example of you guys have figured out how to capture those collisions faster and with intent, not just accidentally. And I think that's fascinating. I did want to maybe circle the conversation to the scientists because I am kind of curious. And I know we haven't talked about this at all, but I am curious when it comes to the scientist. And I'm not a scientist, so I'm going to pretend I'm going to go back to my chemistry and physics labs. There was a process you went through. You had to go through the whole, hypothesis, go through the testing, document. It was a slow process, even in just a chemistry class, let alone in a professional setting. Again, I want to make sure if everyone can see my perspective before my question comes out. If I'm a scientist and I go into an industry, I'm assuming I've attained a certain level of education. I want to solve problems. I want to make these discoveries. I don't necessarily want to do the busy work, but also I've gone through years and years of doing nothing but some of this legwork and busy work. Where does the scientist fit in? Because if the lab is doing their thing and it's self-driving, we're taking note of the data coming out. What is the role of the scientist, and where do they find, I guess, the reason they went into science? Where does that passion lie so that they're getting what they want from the time they've put into it?
Yeah, so what we really believe, especially in this new form of science, will happen is we change the output of the current scientific process. And what I mean specifically by that is currently today, you have 10 scientists that focus on one problem. Let's call it like my research team at the Army Research Lab. And when you actually build self-driving labs that can actually do this work for you, well, now you can have one scientist focused on 10 problems at a time. And that scalability and that impact of having all 10 of those scientists now working on 100 problems versus the one problem they were just solving really leads to exponential growth of novel discovery. And so that's a great thing. So where do they play a role? Intuition, which we talked a little bit about earlier. When you have a lab that is now running all of your ideas, the future world that we envision is when I wake up in the morning and I come to work as a scientist, rather than put my lab coat and my gloves and my glasses on and going in and pipetting new samples and getting them prepared and using dangerous chemicals, instead I'm going to come in and I'm going to talk to an agent who's going to say, "Good morning, Joseph. Last night we ran 107 samples. Of those 107, 17 of them had great properties that you identified as important. Our recommendation would be to run these 100 experiments next. What do you think?" And as a scientist, intuition is what you're going to bring. I would run those 50 and then maybe swap out copper for molybdenum there and then run 50 there. And the AI, this whole process as you continue to do this, is learning and is actually starting to study. Okay, you said to put copper in. Why? And what was the result? And so you start to capture intuition. And in our opinion, that is true knowledge. What makes a great scientist? Someone who's got great intuition around what's coming next from decades of career in scientific discovery. And so we can capture that intuition and actually remove them from the busy work and allow them to have more hypotheses around what they want to do. That is truly what scientists were meant to do in the first place. You don't go to get a PhD to learn to pipette. You go to get a PhD to think about how and why and where the world will change and how new materials can be a part of it. That is what we're going to enable scientists to be able to do in a world that's driven by AI discovery and self-driving lab experimentation.
Joseph, fantastic. Been amazing discussion. I'm even more fascinated now, and hopefully everyone else is as well. I am sure someone will be like, "Hey, Amir, you forgot to ask this question." If there is a follow up, is there a good way, or if there's just interest in understanding more of what we talked about? What are some good ways to learn more, get in touch, etc.?
Absolutely. So first thing, a big believer in cold email. Bias to action is my most important thing as an entrepreneur. Reach out to me. Send me an email. Send my team an email. Joseph@radical-ai.com. And we'd be happy to answer you with what your question is. We make a point to make sure we get back to almost everyone that we can that emails us. Number two, social media. I'm on X. I'm on LinkedIn. Please feel free to reach out there. Let me know. I'd be happy to have a conversation. And then three, you can go to our website and we have a careers page there. So if you are one of the smartest, most ambitious people in the world and you want to work on problems that will impact all of humanity, we are aggressively hiring and would encourage you to reach out.
Fantastic. Joseph, thanks again for the time. I appreciate it.
Amir, thank you so much.
Absolutely. That's it for the episode. Be back again, different guest, different topic. Until then, two things. One, I'd love if you could share this episode. I think Joseph walked us through pretty much the end-to-end of science and how materials get discovered from the way it was to the way it is and the way it's going to be. And we talked about how patents work within both those ecosystems, how mistakes used to lead to science, and now we're talking about reverse engineering what we actually need and want. And also we talked about the scientists and their role in it. So please share this episode with others that might enjoy it. I really would appreciate that. Also, like, subscribe, comment, let me know how the show's going for you. Until next time, thank you and goodbye.